I'm Daze Thomas, Assistant Professor, Department of Artificial Intelligence and Data Science from SNS College of Engineering. Today, let us discuss the topic Input Output Systems of Operating Systems. The main objectives are to explore the structure of an operating system's input output subsystem, discuss the principles of I/O hardware and its complexity, provide details of the performance aspects of I/O hardware and software. Let's move on to the overview. I/O management is a major component of operating system design and operation. Important aspect of computer operation. It is I/O devices may vary in different systems, various methods to control them, the performance management, new types of devices frequent. We'll also discuss the pods, buses, device controllers connect to various devices. Then device drivers that encapsulate device details. First we learn I/O hardware. Incredible variety of I/O devices for storage, transmission and human interface. The common concept is that signals from input-output devices interface with the computer. A port is a connection point for device. Bus is a Daisy chain or shared direct access. PCI bus common in PCs and servers. PCI Express. Expansion bus connects relatively slow devices. Then we have a controller or a host adapter, electronics that operate port, bus, device. These are sometimes integrated or sometimes a separate circuit board or contains processor, microcode, private memory, bus controller, etc. This is the typical diagram for a PC bus structure. In the center, you have a PCI bus, and on one side, you have monitor, graphics controller, processor, bridger, memory controller, cache, memory, and SCSI controller. On the other side, you have IDE, disk controller, expansion bus interface, keyboard, parallel port, and serial port. Then, I/O instructions control devices. Devices usually have registers where device driver places commands, addresses, and data to write or read from registers after command execution. Devices have addresses used by direct I/O instructions, memory mapped I/O. These are the different I/O port locations on PCs. Next, we learn about polling. For each byte of I/O, you have to follow these steps. First step is read busy bit from status register until 0. Then host sets read or write bit, and if write copies data into data out register. Host sets command ready bit. Controller sets busy bit, executes transfer. Then controller clears busy bit, error bit, command ready bit when transfer is done. So we'll see every step in detail. First step one is busy wait cycle for wait for I/O from device. It is reasonable if the device is fast but inefficient if the device is slow. Then interrupts. Polling can happen in three instruction cycles. First one ready status, logical and to extract status bit, branch if not seal. CPU interrupt request line triggered by IO device, checked by processor after each instruction. Interrupt handler receives interrupts, maskable to ignore or delay some interrupts. Interrupt vector to dispatch interrupt to correct handler. Context switch at start and end based on priority, some non-maskable. Then interrupt chaining if more than one device at some interrupt number. This is the diagram for interrupt driven IO cycle. And continuing the interrupt mechanism also used for exceptions, terminate process, crash system due to hardware error, page fault executes when memory access error, system call executes via trap to trigger kernel to execute request. Multi CPU systems can process interrupts concurrently if operating systems designed to handle it. Used for time sensitive processing, frequent must be fast. So that's all for today's class. We'll continue in the next class. Thank you.